In this module of helicopter aerodynamics, we are going to introduce two concepts. First is dissymmetry of lift, and the second is blade flapping. Okay, we know a helicopter has a unique capability of hovering, and now we can see a side view of a helicopter, and it's hovering above grassland. Now let's move to the top view, and we can see the four blades are rotating in a counterclockwise direction. So if we take a look at this highlighted section here, blade section here, and we know the blade has a rotational speed of omega times r, where the r is the radial coordinate of this section. Okay, so now let's cut through that section, and we will have a cross-sectional view of the blade. So now let's introduce a few terminologies. First of all is a chord line. The chord line is a line going through the leading edge and trailing edge of the aerofoil. And also we have the chord. It is the length of the chord line between the leading edge and the trailing edge. Usually we use chord as a characteristic length of the aerofoil. And now we assume the aerofoil or the blade is stationary. Then we have the relative wind with a magnitude of omega times r, which is a rotational, has the same magnitude as the rotational speed of the blade. Okay, now we can notice there is an angle formed between the relative wind and the chord line. That's actually the angle of attack. And because of the angle of attack, there is a pressure force acting on the airfoil, and this pressure force can be decomposed to lift and drag. Then we know the lift can be calculated as CL times half rho v squared times C, and CL can be further approximated as A times theta. Theta is the angle of attack, as already reviewed, and A is actually the slope of CL theta curve. And this is because when the stall, before the stall happens, the CL grows linearly with angle of attack as shown in this graph. Okay, we are getting familiar with the lift generation during hovering. Now let's see another scenario, the helicopter in forward flight. So apart from the rotation of the blades, the blade will move together with a helicopter towards the left. Okay, now in order to help with the analysis, we're hiding the fuselage of the helicopter. If now we see the blade disc in here is divided into quarters. If we now focus on the top blade in here, we can see the linear velocity distribution along the span, and we notice the blade is rotating the same direction of the flight, so we call it advancing blade. And apparently when the blade in quarter 1 and 4, it is advancing blade. Now let's move the other blade, which is a bottom blade, and it will have a velocity distribution symmetrical to the center. And apparently this blade is moving in the opposite direction of the flight, so we call it retreating blade. Okay, and since we know the blade disc as a whole is moving towards the left with a big V, velocity magnitude of big V, and now we have the rotational speed of the blade and also the flight speed. We want to know the total velocity of the blade sections. So still we're looking at these two blades, and they will have a non-symmetrical velocity distribution. And for the advancing blade, usually the total velocity is higher, but for the retreating blade, the total velocity is reduced. And we can expect the highest blade speed at here and the lowest blade speed at here. In the meantime, there are locations in here and there, and they both have the medium blade speed. Okay, so now again we are focusing on these blade sections, and now we have two sections and they're symmetrical towards the center. Okay, and then we know the total velocity for each section. For the top section, for example, is omega r plus v. For the bottom section is omega r minus v. So no, the velocity magnitudes for these two sections, although their locations are symmetrical towards the center, but the magnitude of total velocity is changed. They are no longer symmetrical. Okay, so again, we're cutting through those two sections. We have cross-section 1 belongs to the advancing blade, and the cross-section 2 belongs to the retreating blade. And again, we are assuming the blades are stationary. Then the cross-section 1 is subject to an incoming flow of omega r plus v, and cross-section 2 has incoming flow magnitude of omega r minus v. Apparently, the pitching angle for the two airfoils are the same. Now we can calculate the lift for each of the airfoil. And it's really obvious that L1 is larger than L2 because it has a larger relative velocity and it's an advancing blade. So now we can introduce the idea of dissymmetry of lift. So when a blade is in quarter 1 and a 4 is subject to a increased relative wind speed, so the lift will increase. Only contrary, the blades in quarter 2 and 3, they are the retreating blades, so it is subject to reduced relative wind speed, and then the lift will decrease. I highlighted this part as blue. So in total, the unequal lift distribution between the advancing blade and the retreating blade is called the dissymmetry of lift. So this is a definition of the dissymmetry of lift. And you may wonder what's the outcome of this dissymmetry of lift. So one direct outcome is a blade flapping. And because the advancing blade is subject to an increased lift, so it will flap up, but for the retreating blade, it will flaps downward. Okay, so now let's have a closer look of blade flapping. And what we have again are the 4 blades. And now let's look at this section, highlighting dashed yellow line. We know it has a phase angle of phi, and the linear velocity or the rotational speed of the section is omega times r. And since we want to know the total velocity, we need to decompose the flight vector into flight velocity into two components. We are making use of the component which is parallel with the rotational speed, and it's v times cosine phi. Okay, so now we have this cross-section. We're in a cross-sectional view, and the incoming velocity, total velocity or total wind is omega r plus v times cosine phi, and we know the pitching angle of the blade is theta. And for this blade, analyzed here, it is advancing blade. So according to the analysis earlier, that the advancing blade will flap up. So in this case, there will be a small wind, a flapping velocity going downwards into the stationary airfoil. So now we have the horizontal velocity, and also we have the vertical velocity. The total velocity vector or the incoming flow vector is like this. So essentially, under the influence of flapping velocity, the actual angle of attack will be reduced in here, will change. And okay, so now we have the angle of attack, then we can, it's calculated this way. First of all, we need to find this small angle, then use theta to minus this angle, becomes alpha. Okay, so then further we can calculate, since we have the angle of attack, we can further calculate the lift acting on the aerofoil or the blade. So there is two assumptions actually applied. First of all, it's a straight blade. They have the same chord from the hub to the tip. The other is the same pitch angle. So along the blade, the pitch angle stays the same. Okay, now we have the lift. We also know there's a weight acting on the airfoil or the blade. So then we can write down the simplified blade flapping equation using the Newton's second law. So it is lift minus weight equals mass times the vertical acceleration. Okay, so now it's time to do the summary. First of all, we studied the lift generation during hovering for the helicopter. And then we studied the helicopter in forward flight, and we also defined advancing blade and a retreating blade. And the advancing blade usually is subject to increased airspeed, but for the retreating blade, the relative airspeed will decrease. And so further, because the airspeed is larger, then there will be increased lift in advancing blade. So the same for the retreating blade is subject to reduced lift. So this is called the dissymmetry of lift, because in different quarters for the retreating blade and advancing blade, they don't share the same amount of lift. Okay, then we introduce blade flapping. We calculate the lift and also derive the blade flapping equation, which is a simplified one, but we really need to remember the assumptions we applied, the two assumptions. Okay, that's it.